So I'm going to talk about unit testing. So unit testing is something I've become quite passionate about. And I want to inflict isn't the right word. I want to pass this love on to you. And so for the afternoon lab and for all the labs here forward, you're going to be writing unit tests as part of those labs. This is to help you know that unit testing is not something you do occasionally because I ask you to, but because it is a beautiful way to write the code itself. All right, so what is a unit test? And the easiest way that I can describe it is that it's a small, boring program. It's a program that's so small and boring you would never write it on its own. Except that it also kind of tests to make sure that something happens, that your code performed a behavior that you were actually looking for. Actually, what's kind of nice about unit tests and when you write small, boring programs is that it lets you write a small, boring program and you don't have to think, oh, I'm creating another app and no one would ever run this program. And then that's useful if you say, my program is to I'm developing this class, and I want to see if it compiles. So I'm going to write a unit test that constructs my class, and then it does nothing else. It doesn't even have any testing statements in it. Then you can execute that program, and you can execute that program. That's an option. So for instance, what's an appropriate, or what's an example of a unit test? You could say, create an instance of your class, and then if you call this function getVal, you would want to make sure that returns 3. Maybe the class that you're instantiating needs 3 if it's just been constructed. You can copy one instance of your class into another and then make sure that the two classes have the same contents. You can make sure that your copying is actually succeeding at copying. That's a reasonable thing to test. You can call this function that maybe you pass it 3 arguments, and then you expect the answer to be 7, and you test is the value returned by that function 7. That's a reasonable thing to test. So you can write a function, you can give it bad input, and you can make sure that this function then throws an error message, throws an exception. You catch that exception, and you look at the message in that exception, and it says something in particular. And you compare the string that it returns to against some hard-coded string that you have, which you're expecting out of it. This is really useful if you ever read in from a text file, because anything that the user can give you, the user will do wrong. And you don't want your code. One really useful goal in programming is that your code should never segfault. It can exit on bad input. That's totally fine. And it can give you an error message. It can say, this is bad input. That's great. But if it just segfaults, if it just stops running, then you have little to go on. And users particularly dislike that. So what I like to do is when I'm reading from text files, is figure out all the ways that the text file could be badly formatted, and then construct those badly formatted text files and give them in as unit tests, and then catch exceptions that are thrown by my code, which is then reading that text file and then comparing the thrown exception message with what I expect it to be. Okay, so unit tests answer, they're great in developing code, but they also have this nice property that they give you reassurances for the future that your code still works. And that's really useful, because Rosetta is changing constantly. And sometimes I wake up in the middle of the night worried that all the jobs that I've been looking at the output from have this bug. Like the derivatives were all wrong for all of those jobs, and minimization just failed, and that's why I'm getting the results that I'm looking at. And so it's nice to know, oh wait, the derivatives, they're all right still. They haven't been broken by someone. I can look, I've got the test, compare the derivatives to what they should be, all is right with the world. And they also give you, and I've been trying to make this point, but they shorten your development time. So it used to be that I would sit down and I would write code from beginning to end, and it would take me, say, this amount of time to do the writing. And then I would spend a long time then trying to compile my code, and resolving compilation bugs. And then I would get something that would run, right? But it would be wrong. And so I would spend this amount of time debugging, right? So my development time, I used to think, like, maybe Jack could even attest to this, I would have like a 5-week deadline for this paper. And I'd say, I can write the code in 1 week. I can debug it in 3. And then I've got a solid week that I can write the paper in. And I'm not sure I ever made any of those deadlines. But I definitely knew that it was going to take me much less time to write the code than to debug it. And this was an unfortunate thing for me. And what usually happens is that you finish debugging and you start using your code, and it's not totally wrong, but it's not right. And so you waste a lot of time trying to generate results and understand your results. And then you realize that it's wrong, and then you spend even more time trying to figure out what it is that you've made wrong, right? So if this is like the end-to-end from where you think you're going to start writing your code and where you actually finish writing your code, this is more representative of the amount of time that it takes you to develop code. If your strategy is to write a little bit of code, write the tests for that code, compile your code, debug it so that the tests work. And then you know your code works. You know that this piece of code works because you've written tests for them, and the tests now pass. You write some more code, right? The code that's going to sit on top of it. If you have an onion, you start with the innermost layer, and you make sure that that works. And then you write the next layer out of the onion and test for that code, sort of knowing already that the code in the center of the onion works correctly. You figure out all the compile, the syntax errors in the code that you've just written, so it takes a little while to compile your code, and it takes a little while to debug. And finally, you can do, like, say, the last layer of your onion. So if this were 3 units worth of writing code, you've distributed them out, but you've cut out a ridiculous amount of debugging of your code. Yeah, I'm not at all kidding that now that I've developed my code this way, I can get a lot more code written in a lot less time. I guess when so I was rewriting the matcher back in 2009, let's say, and it's a big project. But I started it at the center, and then had some ideas of what my classes should do, and then started writing tests for them. And I was glad that I started writing tests for them because even though what I thought I was doing at the very center of the code was pretty simple, I did it wrong. And I would have spent a very long time, at the end where I'm like trying to run the matcher and I'm not getting any matches, right? And all that I have to say whether or not my code is working is the number of, like, the quality of the designs that are coming out of enzyme design, right? I mean, that would be like kind of a nightmare scenario where eventually I figure out, I spent all this time, debug. Oh, it was something in the very center that messed me up. So I highly recommend this sort of workflow in terms of how you want to develop your code. Okay, so the 2 big questions: how do you create a unit test, and then what is a reasonable unit test? Okay, so the how in Rosetta is through this test suite package that we have called Cxx Test Suite. I always wondered what the X was about, whether it was like hidden or something, but if you turn your head, it looks like a plus on its side. I think that's what's going on with Cxx. So it's the Cxx Test Suite. This is a base class, and what you're going to do is you're going to derive a new class from it. So you say my class tests, and it'll derive publicly from, in the namespace, Cxx Test, Cxx Test Suite, and then you'll put some things inside this class. So this is going to be your suite of tests, and then each unit test is a function that returns void, that's named beginning with test underscore, and that it should take no arguments. So this would be, say, a valid declaration. So void test underscore my class underscore default underscore ctor for the constructor, right? So that's a fine way to declare a unit test. One thing that I like to point out here is that C++ doesn't care about your white space. So you can have void on one line and then test on the next line. But the script that's going on sort of in the background to take the declaration that you have for your unit test suite here and convert it into something that'll actually execute does. So if you put test on the next line, it won't find your unit test and it won't run it. So that's one thing to watch out for. What I like to do is to make sure that my tests fail from time to time. Like I'll put in some condition that should not be true. And I'll get to it later, but you can say, this condition should be true. And you can put any condition you want. But one condition that's never true is false. So I like to put that in occasionally, and that makes me aware of the fact that, yes, my unit test is running. Okay, so how are you going to do it? So you're going to save your code in a file. So in the Rosetta source directory, there's the test subdirectory. So often we have you looking in Rosetta source and then the src subdirectory. That's where all the code that you've looked at so far lives. But in the test subdirectory here, and this is not to be confused with the integration test directory, which is sort of in a different place altogether. Then you have, say, a subdirectory of that core that mirrors the directory in the src directory, scoring that would mirror that directory, and then this would be the name of the file, my class, if you declared some class in core scoring, and then it finishes with cxxtest.hh. So if that's where you declared your class in source core scoring, then this is where you would put your unit test in test core scoring. You add the word my class to this core.test.settings file found in the test directory. So a lot like the utility.source.settings that you see in the source directory. There's a corresponding utility.test.settings or core.test.settings file in the test subdirectory. So if this were the scoring, so if I've got a snippet of this file, here's a scoring directory, and I would add my class just to this list right here. So in between E and R there. Right, and so there are these equivalent files again for each of the libraries that we have. Then I told you earlier you could say to the unit test suite, this condition should hold, and that's done with this this function or macro, TSS or TS underscore assert. I think TS stands for test suite, and then the assert is kind of similar to assertion statements that you'll see elsewhere in the code, like asserting boundary conditions for arrays. And then condition here is some expression, and it can be anything. So if it evaluates to false, then the unit test suite will report a failure. It won't crash. It'll just say this test failed. So if you run all the unit tests, then if one of the tests fails, it'll report it at the end. You had one test failure. So for instance, this condition can be anything. So if you want to call the getVal function of your instance of my class, you could assert that it equals 12, right? Maybe that's a reasonable value for getVal in some given some preceding lines of code. For instance, you could also say if you've caught an exception, you can ask for the message that comes with that exception, and you could compare it against some string. So there should be a closing quote here, but you could compare it against that. That's a fine condition also. You can also say that two floating point values should be near each other within some epsilon. Sorry, Jack. So Jack hates epsilons. For instance, you've got val1 and val2. You might assert that the difference between them is, let's see, greater than epsilon would be kind of a weird way. I'm sorry, this should be less than. If they're within, nope, I didn't read the rest of the line. So if it's greater than epsilon, then the unit test is reported as a failure. If it's less than epsilon, then it passes. Okay, there are two useful functions that are defined for that the test suite will invoke for you before every one of your unit tests gets executed. One is called setup, and it's called right before the test is executed. The second is called tear down, which is called immediately after the test is executed. So setup could be something like if you had a pose and you wanted it to be initialized freshly at right before every one of your unit tests, and was the same for all the unit tests. Then you could initialize it in setup. That would be a fine thing to do. And then tear down could be something like, if you had, like, say, a pose owning pointer, you could initialize that owning pointer to a fresh pose in setup, and in tear down you could point it to 0 to make sure it got deleted before the test suite exits. You shouldn't put code into the constructor, because these test suites are actually allocated before most code is ready to be executed in Rosetta. Right. So here's an example. So if I've declared my class in namespace core scoring, then I'm going to initialize it according to some val, and I can get the val with this accessor, and I can set the val with this setter. And so my unit test would be something like, I just want to make sure if I give it the parameter, this is my class. It derives publicly from Cxx Test Suite. It calls core init when it's set up. This is something that's fairly common. And this is defined in these init utils within the test architecture. You'll see them everywhere, so that's not a hard file to find. And then here's a valid unit test. So void test the parameter constructor, right? So I'm going to call this constructor. And so I'm going to initialize my class with the value 5, and then I just want to make sure that it actually has the value 5, right? So it's a totally reasonable, I mean, this may seem trivial, but it's like a fine thing to test. There's no reason not to test this. What do you think this would do?
Not 5. Fail, right?
So what do you mean if it's not 5?
You're passing 5, right? Should be, you're instantiating your object.
Uh-huh.
Value 5. And you're adding 1. What? Adding 1. Oh. So this is going to fail.
It's going to fail. So it caught a bug. So I meant to just set it to the value, but I didn't, right? Because I got, I don't know, a little crazy, and I just started adding 1 to things, right? So this would fail, and it would actually alert me to a bug in my code, right? So there's some virtues here. First, let's say I fix this bug, then this unit test would continue executing in the future to make sure that I didn't go crazy and started adding 1 again in the future. But it also it forces me to kind of sit down and say, what behavior do I expect of this class? Right? I actually have to encode that. And so that's the second virtue that testing will give you. Yeah?
So more like a conceptual question. Let's say you did a lot of operations in your class. How much coverage should you aim for in your unit test? 100%, which would be a lot, or 80%? What's the rule?
The more tests, the better, right? It's hard to say that you have too many tests. If you were to say execute this test, it would take a very small fraction of a second to do. So if you were to write 1,000 tests for your class, they would probably be fine, right? 100% test coverage would be wonderful, and so I would say always aspire to that.
Because it's hard if you like logical statements that don't always.
Yeah.
Rarely do you reach certain parts of it.
Yeah, but where else are you going to test that functions correctly, right? Let's say it's actually really hard to construct the case where you hit this block of code, and you don't and as you're writing it, you're not really sure what will happen when it hits that code because you haven't constructed that case, right? Do you want to deploy that code on, say, like a huge cluster, like thousands of computers are running this code, and you're thinking, I wonder how many of them are going to crash, right? So one of the awesome things about unit tests is that you can figure out what you need to give as input to a function that'll hit that rare case, come up with that thing, and then give it to that function, right? And so then you can hit all the edge cases. So that was a really great lead-in to the question, which is, what should you unit test? And so everything tricky, you really want to unit test. So the edge cases, the pieces of code that you rarely operate on, those things are like what's crying out for being unit tested. Construct the example that makes this thing executed. It would be very difficult to do that in the integration tests, partly because they only run for so long, and partly because you don't necessarily know the trajectory that you're going to get through the integration tests, right? Whereas if you, in the unit test case, you can start your function that has these tricky edge cases with the inputs that are exactly going to push it off into that portion of code that you know is tricky and that you need to be needs to be tested. So any complex mathematical functions, I would recommend unit testing, especially at edge cases for those mathematical functions. Any data integrity issues. So usually when you have a class, you're trying to keep two pieces of data in sync with each other, two or more, right? So for instance, class pose has an energies object and it has a confirmation object, right? And I just talked to you about how scoring is going to grab this domain map out of the confirmation and use that to figure out which edges to drop. And so the confirmation and the energies object, they have to be kept in sync, and the pose is responsible for that, that task. So it's got this data integrity issue that it needs to deal with. And so so you would definitely want to have unit tests for things like that. There are, I guess I can say with high certainty that at some point you'll have a bug where you have X and Y that you wanted to have some relationship to each other, and you changed X without updating Y, and then that relationship no longer holds. And it's just a little tricky to come up with an example of what exactly that will be, but I've been there and I just have fuzzy memories of them, usually because I'm a little blurry-eyed after hours of debugging and nothing is coming through very strongly. Okay, so and then I definitely recommend unit tests for handling bad input. Well, if you're ever dealing with the user, I would think of them as being sort of the lowest common denominator human being ever, like capable of reaching the keyboard. So they're going to do everything wrong that you want to. They really will. And so if you write code that's set up to handle their errors, then you'll be in much better shape, and you're less likely to have crazy seg faults.
So it's just like, what you mean, let's say a user has 3 arguments to a function, they have to be, an int and a double. So
In particular, I'm thinking of the user that's sitting at the command line and typing in a text file, and they're going to provide that text file as input to the executable.
Okay, so let's say you have to parse it. And it has to be parsed into an int and a double. So would you write 3 separate unit tests to check that the first element in RC or RV is an int, the second is double, and the third is double? That's not people with.
You probably do it all in one test, or you just have 3 asserts.
Or do it all in one.
Well, I mean, so you would write a unit. So your code should make sure when it's trying to read like the first int that it is an int, and then it should throw an exception if it's not. And then it should try to read the second int, and if it's not an int, then it should throw an exception. And if it tries to read the third double, it's not a double, then it should throw an exception. And so you would actually have to construct 3 different input files, input strings, if you will, and then have those strings be wrong for each of the files in as many ways as seems reasonable. Catch those exceptions, and then assert that the message is what you expected. Really, and then so definitely everything tricky, and then really anything, right? I mean, you can write unit tests for trivial little things like this my class constructor, which actually had some glaring flaw that I might not have noticed, or any function that you write that you want to have this behavior, and you want it to continue having that behavior, maybe because your scientific careers depend on it. And so if it should ever stop having that behavior and that would mess you up, then you want to write a unit test, right? Because it's one thing for someone to come along and change a piece of code so that it no longer functions. It's an entirely different thing for them to come along and change the unit test that goes along with that code that says, this should be the output. And you're like, well, I don't think actually that should continue to be the output. Like, for instance, there's the superimpose mover was like the main functionality was commented out because it returned this RMS, and it was stored in a variable, and the variable was never used, and so people who were cleaning up warnings wanted to get rid of unused variables, and so they commented out the line where it says it says float RMS equals superimpose pose A to pose B, right? And the RMSD of that operation never got used later, so that whole line was commented out. But that was the meat of the function, right? And so the superimpose mover stopped superimposing, right? That's kind of a big deal. Somehow that code, well, I don't know. It either snuck in twice or people were using the old version, but that bug has been raised a couple times on the forums, right? So if you're really interested in making sure that your superimpose mover is superimposing, then you want to write a unit test that does that.
Do you always run this at runtime? The unit test?
Well, they're a little program.
So it's part of the program?
Well, I mean, they're a separate little program. I mean, they're a little executable. So you would run that little executable, and it so everything is only runtime. Yeah, it's not something that you could just statically analyze. The way you, like, for instance, when the library levels test is executed, it's just looking at all the pound inclusions, right? It's not compiling the code or running it.
But do you run, every time you run your program, do you also run the unit test to go with it? Is that
Every time you commit, you should run the unit test before you commit. Yes.
A little bit more related with the movers. So if you want to write a unit test, let's say for your complete mover, should you write also like constructor just for that unit test, or do you need? Or there is a method to use the parse XML tags to call the mover.
You can do whatever you'd like in your unit test. You can use you could create a tag object from an XML string if you felt like, and then pass that tag object to the mover factory or to some other thing which turned tags into movers. If that's something that you were interested in, sure. That's a fine way to write a unit test. You can also just create the mover that you have in mind. You can say, my mover MV, right? Yeah.
Why are the unit tests separate? Why aren't they just in the code itself?
Well, in some ways they are in the code themselves. Right? So they're part of the Rosetta source directory, and so they don't get split from it.
But they're not like, okay, you run this function, and right after that you test whether the outcomes are actually expected. If it doesn't, it just gives you an error message or whatever.
Sometimes that's well, it's often because it's difficult to figure out what the right answer should be. Sometimes it's difficult to figure out. Well, let's take minimization for an example. If you say something abstract like, when I start minimizing the pose, it should end up at the nearest local minima in confirmation space from where I started. But that's a nice way to formulate the question, right? But it might be difficult to know whether or not the pose made it to the nearest local minima. Like, you'd have to know the energy landscape to figure out which one, where are the minima, which one is closest. That's a difficult question to answer.
The question is more related. That's what I understood. That you need to have a separate file for the unit test, right? And I think the answer is because this C++ module for the testing is a heuristic method that will automatically detect the test and build the program to assert if it is passing the test or not. So it's a complete separate module of C++ that has been made to test C code.
So yeah, I mean the build commands and scans are different using the Cxx Test Suite. I don't know of any test suites that would say integrate directly with the codes themselves. There are more complicated things like assertion statements that you can put in the code, like at the end of this function, this should be the answer. But without, I mean, without executing the code itself, it's sometimes difficult to know what the right answer should be. And so the unit tests, when you're writing a unit test, you actually have to figure out the answer. So it's up for the it's up to the programmer to decide what is correct, or to reason out what is correct.
Andrew, if I have a big hairy program say it's a mover, right? It has a public interface of apply, but it has all these private methods, all these private data, and I want to test that. Should I make all that public, or what should I do?
That's a great question. I'm glad you asked that question. So one way you could approach it is you've got this class that has a lot of private data, and you want to test, or a lot of private functions that are interacting with this private data, and you want to test that sort of subsection of functionality is operating correctly on its own. And one way to do it would be to not have a big class, but have little classes, each with small responsibilities. So if you've got, say, a group of little things of private data that belong together and that have like a certain data integrity rule amongst them, you could have a little class that wraps just that data and that provides a public interface, right? And then you can test the code using that public interface. If you have that class as a private data member of what used to be your big monolith, then it's not presenting that interface to anyone who's using the monolith, right? It's still private, and so it's still sort of keeping that away from the user. It's not something that the user would necessarily see, but you could test that class using public functions. A less good answer to that question, which I've given before, is that you can actually change the meaning of the word public. I shouldn't tell you this, but you can pound define, like, have you seen pound defines before? They're like declarations of macros. So you can pound define public to be, well, you can change it. But maybe what's more, I'm getting it backwards. You can pound define private to be public. Yes, Brian was very interested in this solution to the problem that he had in testing like a small thing. And I think maybe the better solution is to extract the data that belongs together into its own class instead of, say, is a private method of the class. Yeah. But maybe it could be a private method that calls a public method of another internal class. And then that would get past this issue of testing private methods. Right, so certainly any function that you want to behave a certain way, like because it's important for you that it continues to behave that way, you want a unit test. Especially if someone breaks your code, right? So anytime that someone commits a change to your code that makes your code stop behaving, then you need to go back and write a unit test, because it's not good that your code broke in the first place, but it's even worse if it broke again for you, right? Imagine explaining that to your advisor. Yes, superimpose, stopped working again. Well, it seems like you could have seen this coming. Fool me once, shame on you. Fool me twice, shame on me. Okay, and then I think maybe the end of these slides, or is this out of juice? Okay, no, I think that's the end. There's a lab 4 that I think has been shared with you, or I hope has been shared with you. Is that good?
Right?
Yes.
Okay.
Excellent. Enjoy.